Hello, everyone. Greetings and welcome back to another Math 104 lecture. So today what we are going to be looking at is the coordinate plane. So the coordinate plane is essentially when you have, two different number lines kind of overlaid on top of each other, right? We're used to, so far, we've seen one number line, just so one dimension, something like this. And we know our number line is, the positive numbers, so everything to the right of 0, so on and so forth, and our negative numbers that go on to negative infinity to the left of 0, right? Well, if you look at our coordinate plane, it's going to be the exact same thing, but it's just going to be two of them. So one is horizontal, and that's kind of how we've seen the number line so far, and the other one is going to be vertical. And what the coordinate plane allows us to do is it allows us to plot ordered pairs or points onto our plane. So a point or an ordered pair is just going to be something in the form of AB, where A is going to be your x component, so your x-axis. So that's going to be your horizontal component, and B is going to be your y-axis component. So that's your vertical component, okay? So for example, let's say I just wanted to plot 3, 2 on my coordinate plane that I already have existed. Well, 3, 2, again, the 3 is in reference to the x-axis. So that means we're going to go 3 units to the right on the x-axis, and 2 is referencing the y-axis, so that means we're going to go 2 units up onto the y-axis. Okay, so we see that we're at 3 on the right and 2 going up, so we would end up right about here, and this would be our point. Sorry, there we go. And this would be our point 3, 2. Okay. So again, it's not so bad. Just realize that x is always going to come first. So when you're reading an ordered pair, your x-axis is the first value, your y-axis is the second value. Okay, please do not try not to confuse yourself. We've obviously seen things sort of with similar notations. We've seen 3, 2, for example, as a notation for being an interval. And what do I mean by that? Well, an interval being like, okay, well, if we're starting at 3, this is probably a bad example. Let me flip the numbers. There we go. That's a better example. So we've seen this sort of thing before, especially in our last couple lectures that we talked about when we were dealing with inequalities, where the solution we found was actually an entire interval, right? So we've seen this sort of notation before where, you might be referencing the interval between 2 and 3, and it would look something like this, right? Well, when we're talking, and obviously open circles because parentheses imply you're not including the endpoints, right? Okay. Well, when we're talking about ordered pairs, just keep in mind that we're talking about the numbers having a specific definition tied to each axis. So in this case, again, 3 is not saying you're starting at 3 and we're looking at the interval between 3 and 2. 3 is referencing how far along the x-axis we're going and also in what direction, right? Positive 3 means we're on the right side. Negative 3 would mean we were looking at the left of 0, right? Same thing with 2. So 2 being positive means we're looking up the y-axis. Negative 2 would have meant that we're looking down the y-axis. Okay, so with that being said, the coordinate plane is actually split into 4 different sections, as you could probably see, right? So we have 1, 2, 3, and 4. And we actually go in this order with our first, and we call these quadrants. So it's going to be a section of the graph. So our first quadrant is in the top right corner. And then we go counterclockwise. So we go in this direction to continue labeling them. Okay, so again, 1, 2, 3, 4, counterclockwise, starting from the top right. And your quadrants will actually also give you a little bit of insight as far as what the signs are going to be of the numbers. As you can see, we had 3, 2, our point here, 3, 2, that we started with. That was both positive, right? Any point that's in the first quadrant, both values are going to be positive. And then you take a look at your second quadrant and you say, oh, okay, well, that means that anything. So if I plot some random point over here, I don't even care what it is. I'm just putting a point over here. If I put some other point in the second quadrant, you'll realize, okay, well, the y-axis is still going to be positive. The x-axis is negative now. In the third quadrant, we have and again, just plotting some random point, both of the values or both of the components are going to be negative. And in the fourth quadrant, we have negative y values, but positive x values now. Okay, so in another way that you can think about it is that whatever the sign is of, one quadrant, the quadrant that's directly diagonal from it will have flipped signs. So again, we see that in the first quadrant, our point here, which I'm going to circle in black, it has all positive components, right? Again, 3, 2, it was positive 3 and positive 2. But diagonal, the quadrant diagonal from quadrant 1 is quadrant 3, and circling it in red now, we see that this has all negative components, right? It's negative y and also negative x. Okay, so that's just a brief crash course in coordinate planes and ordered pairs. I imagine many of you have already seen this before, but again, just a quick refresher, getting you back into the groove of this. And if you haven't seen it before, then, well, here's your introduction to it. Okay? All right, so say I wanted to, and we're just going to try to get rid of all this nonsense that I started drawing because I want to clean this up. There we go. Okay, say I wanted to plot some of the following points here. So just giving us a little bit more practice as far as plotting points or ordered pairs. So say I wanted to plot the following points. We'll say A, oops, meant to be in black now. A is going to be 0, 2. B is going to be negative 3, 4. C is negative 3, negative 3. And D is 4, negative 1. Okay. So let's say we wanted to plot these. Well, once again, to plot them, you're just following the components, right? So if x is always first, well, starting with A, your x component of A is 0, which means you haven't gone anywhere. So you're just stuck right in the center. And then your y component just tells you how far up or down you're going from the center, right? So since we're going positive 2, that means we're going up 2. So A is just going to be this point right here, and we can call it A right there. Okay, B is negative 3, 4. So once again, negative 3 implies we're going to the left of 0 on the x-axis. So we are at here now. So we're starting there from negative 3, and now we have to go up 4 units. So negative 3, 4, which is going to be just about here. And this isn't exactly drawn to scale, as I'm pretty sure I spaced out the x's a little better than I spaced out the y's, as far as the, between 1, 2, 3, and 4. But it's, close enough for you to get the idea, right? We went negative 3 units to the left and then up 4 units on the y-axis. So this would be B. C is going to be negative 3, negative 3. Well, that means that we're going 3 units to the left, so to the left of 0 on the x-axis, and also 3 units down on the y-axis. So that's going to give us a point just about here, and we can call this one C. And finally, D is 4 units over on the x-axis and 1 unit down on the y-axis, which is, I'm just going to make the 4 a little bit smaller. There we go. So our point is going to lie somewhere right around here, 4 units to the right and 1 unit, downward. Okay, and we would call this D. So notice that we have 4 points, but only 3 points of those 4 are actually laying in quadrants. The ones that are laying in quadrants are B, C, and D, with B being in the second quadrant, C being in the third quadrant, and D being in the fourth quadrant, right? Our first quadrant being in the top right, quadrant 1, you might think that, oh, A is in both quadrants, 1 and 2, because it lies on the y-axis, right? You'd actually be incorrect by the way that we define being in a quadrant. If your point lies on a particular axis, whether it's the x-axis or the y-axis or both for that matter, and if it were lying in both, the only point where it could do that would be at 0, 0, which would be like, right there, right? But if it were lying on a particular axis, it does not belong in either quadrant that it might appear like it, it might be tied to. So again, while you might think that point A is in quadrant 1 or quadrant 2 or both, it's actually in neither, okay? And that just comes down to the definition for how we've defined points laying in quadrants, okay? So again, just a brief crash course into how we plot points on a graph and what this actually means for us. All right, so let's go ahead and clear this canvas and move on. Okay, so there's three specific formulas or theorems that we're going to look at today. The first one is regarding distance between points. Okay, so we're looking at distance formula. Now, if we're talking strictly about one dimension, so, again, one dimension is just the number line. So I'm going to put 0 here. Let's say we had -2 and 3 over here, right? And I said find the distance between 3 and -2. Well, the distance between points on the number line with, only one axis to consider, well, that's just going to be the difference between the two. But remember, distance can't be negative, so it's the difference between the two, but it always has to be positive regardless of the order that you pick. So you would say, okay, well, the distance is equal to the difference between 2 points and then the absolute value of that, right? So in this case, we would have, all right, well, we would have the difference between 3 and -2. Well, the difference between 3 and -2 is the absolute value of 5, right? 3 minus a -2 is the same thing as 3 plus 2, so we get 5. And the absolute value of 5 is just 5, right? And now notice, because of the absolute value, it actually doesn't matter which order we put our points in. It's going to take care of it regardless, right? So I'm going to do this again, same points, but I'm just going to flip the order. So if we had the difference between -2 and 3, well, -2 minus 3 is -5, but it's inside the absolute values, which still just makes it 5, right? Okay, and this should make sense because you're talking about kind of the distance between the points, but it's the number of integers between them, right? It's the units between them. So you would have from -2, it would jump to -1, so that's 1, then to 0, that's 2, then to 1, and that's 3, 4, and then 5, right? So we can see that the number of jumps that it takes is 5, so that's kind of how we define distance between points. And that's specifically for when we're only considering one dimension, okay? So when we're only considering along one specific line, or one specific axis, I should say. Okay, well, what happens when we're starting to consider two axes, as we just showed, with the coordinate plane? Well, for the coordinate plane, it gets a little bit more tricky, but not terribly so. So let me clear this off. Okay, so the distance between any 2 points, and we're going to call those points P and Q, just for the sake of it, okay? So the distance between P and Q is given by the following equation, and it's going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. And again, it's the square root of that whole thing. Okay, so what are x2, x1, y2, and y1? Well, if we're talking about P and Q, we know that P is going to have some sort of x components, right? So we'll call it x1. And it's also going to have some sort of y component. So we'll call it y1, not y2, sorry, y1. And then the same goes for q, right? So q, but we know that they're different components. If they're not different components, then it's the same point, right? Because then p and q are the same point, so that means p is equal to q. So then the distance would be 0, because when you plug it in, it wouldn't go anywhere. There is no different distance between, a point in itself. So q is going to have different x and y components, so we'll just call those x2 and y2. Okay, so what is this telling us? Well, this is telling us that if we take the difference of the components, we then square the difference and add it together and then take the square root of it, we'll have the distance between the points, regardless, if they're on the axes or not, right? Where are we getting the square and the square root from? Well, remember, going way back, when we were first discussing absolute value, we found this alternative definition of absolute value. The absolute value is really the same thing as if you have the square of x and you square root it, right? Remember, we got this definition from saying, okay, well, we only care about principal values, right? Principal means positive. Well, if you look at this looks very similar, right? Essentially what we're doing is we're squaring the difference of each component because we want to make sure that it's positive. And then we're taking the square root of that because we squared it, right? So we're taking the square root of the square, which should undo what we just did to it. the operation that we did. Essentially, we're just trying to make sure that regardless what order we plug in for x2 and x1 or y2 and y1, that we are that it's going to be positive. Now, there is one specific thing that you should be very aware of, okay? Notice how the subscript 2 is coming first, right? It doesn't actually matter if you call the components of P x2 and y2 and the components of Q as x1 and y1. What's important is that if you choose Q, so in this case Q as x2 and y2, if you choose Q to have the starting value, right? So the starting value here is x2, then it must also have the starting value for the y component as well. Okay, if you choose P to have the starting value, so let's say we rewrote this and we had, okay, the distance between P and Q is equal to the square root of, if we chose the components of P to go first for the x value, so x1 this time minus x2 squared plus, well, that means that your y component of P also must come first, okay? Just be consistent. If you're doing the x component of some point, in this case P first, then you also have to do the y component of that same point first as well. So y1 minus y2 squared, okay? So again, just keep in mind the subscripts what that would mean for real numbers when we have, when we do an example here, is that because you chose this one to go first in the x's, that means you also have to choose this one to go first for the y's, okay? Or vice versa if you made Q go first. Okay, so let's go ahead and look at an example and see how we can actually apply this, okay? So what I'm going to do is I'm going to keep the equation that we have written right here, because I know that the equation might, seem a little daunting at first, but it's really not so bad once you realize all you're doing is you're taking the difference of each component, squaring it, adding it together, and then square rooting it, okay? So let's go ahead and see an example. What I want to do is I want to find the distance. So find the distance between P and Q, given that P is -2, 1, and Q is 3, 2. Okay, so let's find the distance between the two. Okay, well, we know again that the distance between points is going to be given by the square root of this big long expression. And now we can choose either point to come first. However we define this is up to us to be, x2 and x1. We just have to, make sure that we're consistent. So in this case, what I'm going to do is I'm going to make P to be x2. So we're going to say, okay, you're x2. And since -2 I'm choosing to be x2, that means 1 must be y2, okay? And then by definition, because we chose that to be the second, set of points, or the, the second ordered pair, this one is going to be x1 and this one is going to be y1, right? So now all we have to do is just plug into our equation. So plugging into our equation, well, this means that we have x component minus the other x component, right? We're choosing x2 to go first. We're choosing P to go first. So we have -2 minus 3 squared plus, and now we have the y components. And now again, because we made -2 go first in this parentheses, we have to make 1 go first in the other parentheses. So we have 1 minus 2, right? The 2 is coming from the y component of Q. Okay, so now we square this, and now we just have to do our regular calculations. So -2 minus 3, well, -2 minus 3 is -5, so we have the square root of -5 squared, plus 1 minus 2 is -1 squared. And now we have a great example for why we see we're squaring things and then taking the square root of it after we're done. We're squaring things because we want to make sure that they're positive. We're taking the square root because we are then undoing the square that we applied. Okay, so now we see we have the square root of, well, -5 squared is the same thing as 5 squared, right? Because the two negatives would cancel. So we would have 25 plus -1 squared is just 1 squared, so 1. And hence we get the square root of 26 is going to be our distance. Now notice, I really want to hammer this down because this is going to be a big key difference with, something else that we do towards the end of this video. The answer that we got from distance is a number. It's a particular number. In this case, we got the square root of 26, but either way, it's still a number, right? It's not an ordered pair. When we look later on at midpoint, the answer that you should get should be an ordered pair. And this should make sense because if we're talking about distance between 2 points, and if you're talking about, the distance between, say, your house and the grocery store, you measure that in, like, let's say miles, right? So if your house is right here, and so house to the store, right? You're not talking about an ordered point between you and the store. You're talking about, for as far as distance is concerned, how long it takes from you, or the distance it takes from you from your house to the store. So in this case, if this were P and Q, the distance would be square root of 26, right? So square root of 26 miles, or however, whatever unit you were talking about. Okay. Again, I really just want to note that you're getting a particular value here, not a particular point back. So distance is going to return to you a number, and if you don't get a number, that means that you messed up something along the way, or you wrote your equation wrong when you're doing this. Okay. And now, once again, I just want to reemphasize that it doesn't matter which point we chose to go first. So as we can see here, we chose P to be the numbers that, went first in each parentheses. We had the -2 and we had the 1 go first, and that was from point P. Well, I want to do this one more time and show you that it really doesn't matter that you could do Q first as long as you remain consistent, right? As long as if you're putting Q first for the X component, you're also doing Q's Y component first as well. So the distance between P and Q is the square root of, and now we're going to just flip the order, right? So we're going to do 3 first, and then the 3 minus the -2 instead. So we have 3 minus -2 squared plus, and now we have, oops, sorry about that. And now we have 2 minus 1, right? Because we're making Q go first, now we have this 2 minus this 1. And so that means we're going to have over here 2 minus 1 squared. Okay, so doing our calculations, we got the square root of, 3 minus a -2 is the same thing as 3 plus 2. So we get 3 plus 2, which is 5 squared, plus 2 minus 1 is just 1 squared. And we realize that this is, yes, of course, going to give us the same exact thing as when we had a -5 and a -1 being squared. So we get the square root of 25 plus 1, which is the square root of 26. We arrive at the same exact answer. Okay, so again, long story short, you can pick either point to go first for the components as long as you remain consistent. If the component of P for your X is going first, then the Y component of P also has to go first. Vice versa for Q. Okay, all right. So let me go ahead and get you started on your classwork assignment. So this is, let's see here. Okay, I want to do one more example of distance, and then we're going to go over classwork assignment, the first one, but I need to go over one more topic before then. So sorry, I just jumped the gun. Okay, so let's say we had, and I'm not going to use the ruler for this, so bear with my approximation. Yeah, it's not horrible, to be honest. Okay, so let's say we have a right triangle. Okay, so I'm going to say my points. So I have B here, 1, and this is 2. I have A here, and moving along the x-axis, 1, 2, 3, and 4. Okay, and we have C right over here, right? So this is a triangle, right? And I guess now I will actually use the ruler because otherwise this is not going to end well. Okay. So yeah, we see that we have a triangle here, right? And I'm going to say that this is a right triangle, okay? I'm just going to give you that piece of information. And we know it's a right triangle given by this little box in the corner here that's at the angle ABC. So you see it's, that little box that's right by the B coordinate. That's how you know that this triangle is a right triangle. Okay, so given this information that we have, what I want to do is I want to find the distance of AC. So the distance of AC is going to be this side right here, right? Going from A to C. And so what I want to do is I want to try to find the distance of that. So let's try to find the distance of it again using the distance formula one more time. So we have the distance from A to C. Well, this is going to be the square root of, Okay, now the hardest part of this is really just pulling out the information from the graph. What is my ordered pair point for A? Well, for A, keep in mind we're on the y-axis, which means that our x component hasn't moved at all, right? Our x component hasn't gone to the right, it hasn't gone to the left, so we know that this is 0 for x. And we've gone up 2 units, so it's 0, 2, right? And now for C, well, C has moved 4 units to the right, so that means that we have an x component of 4, but 0 units in either direction, up or down, right? It's still just on the x-axis. So that means that our ordered point is 4, 0. And now all we have left to do is just plug in, right? So I'm just going to make C my, the components that go first. So that means I'm going to have 4 minus 0, 4 minus 0, right? The x component of A is 0. So 4 minus 0 squared plus, and now we have 0 minus 2 squared. 0 is my y component for the point C. And again, because we made 4 go first, we now also have to make 0 go first in the second parentheses. So we have 0 minus 2 squared. Okay, so now we plug this in. We get 4 minus 0 squared, which is 4 squared. So 4 squared is 16 plus 0 minus 2 is negative 2. And negative 2 squared is the same thing as 2 squared. So negative 2 squared is 4. And so now we have the square root of 16 plus 4, which is the square root of 20. And we know that we can simplify the square root of 20, right? And how do we simplify the square root of 20? Well, again, just as a refresher, you're trying to factor 20 such that one of the factors will be a perfect square, right? So that way you can do some cancellations. So square root of 20 is going to be the same thing as square root of 5 times the square root of 4, right? And square root of 4 is going to just cancel to give us 2. And so we get 2 square root of 5. So we've now shown that the distance between A and C is 2 square root of 5, which means that the length of side AC is 2 square root of 5. Okay? Again, the distance between 2 points is the length of that line segment. So I'm just hammering that down for you now, so that way the next thing that we talk about will make a little bit more sense. So we get 2 square root of 5. Okay, so I mentioned that this is a right triangle. And now the next thing that we're going to talk about is we're talking about the Pythagorean theorem. What is the Pythagorean theorem? I cannot imagine any single one of you have never seen this or at least heard it before. The Pythagorean theorem is as follows. We have a squared plus b squared is equal to c squared. Okay, and again, I'll just write it over here. This is the Pythagorean, and I'm going to abbreviate it, but Pythagorean theorem, okay? So a squared plus b squared is equal to c squared. You might have seen it in the opposite order. C squared is equal to a squared plus b squared. Either way, same thing. Okay, so what does this relate to? What are we talking about here? So the Pythagorean theorem relates to right triangles. So a triangle with a right angle. And as we saw up here, we had that, right? Because again, we had that right angle notation, that box in the corner where the point B was. So, and I kind of just want to emphasize that a little bit more. So let me draw that in red, just so everybody understands what I'm talking about. So that piece right there. So that's the notation that tells you that we have a right angle at that location. So the Pythagorean theorem relates to right triangles in the sense that A, B, and C are all going to be sides of the triangle, where A and B are going to be the smaller legs, so the the legs that are the the smallest pieces of the triangle, and C is going to be the hypotenuse. The hypotenuse is going to be the longest leg, and the longest leg is always opposite to the right angle. Okay, so if we see here, we're looking back up at our triangle here, our triangle ABC. We see that the hypotenuse is going to be the side that is opposite of the right angle. So the side that's opposite the right angle is side AC. So right here, the side that we actually just solved for, where the legs are going to be AB and BC. And it doesn't matter if you call AB A and BC B or other way around. So you could call AB A and BC B, or you can call them vice versa, AB B and side AC as A. Either way, it doesn't matter as long as, once again, you remain consistent and you understand that this side is always going to be side C because it's opposite the right angle. Okay? All right, so how is this going to correspond here? Well, if we have a right triangle, this theorem here is always true. And actually, this theorem will help us out a little bit later because this theorem is going to emphasize for us whether or not a triangle is a right triangle. They actually imply each other. So if a triangle is a right triangle, then the theorem is true. And if the theorem is true, then the triangle is a right triangle. So you could prove that any triangle is a right triangle if this theorem works out. Okay? So how is this going to come into play here? Well, what I want you to do for your first classwork assignment is I want you to try to find the side of side AC, but this time using the Pythagorean theorem. Okay? So what does that mean? Again, what that means is we're solving for C using this Pythagorean theorem right here. So you have to, using the information from the graph, figure out the length of side AB, the length of side BC, and then you plug in, and then you're going to be solving for your missing side, which is the hypotenuse. So solve for the same exact side, but this time using the Pythagorean theorem, and see if you can figure it out. I know that I didn't do an example before this classwork, so I just want to see if you can, extrapolate and get this one on your own. Okay, so hopefully that wasn't too bad. So what are we doing here? Well, the idea is first, before we do anything, we need to get the lengths of each side, the lengths of our known values, right? We don't know because, again, you can ignore the work that we did over here with the distance formula. Assuming we didn't do this, we don't know how long side AC really is, right? Which is, we call this our C. This is our unknown. So what we can do, though, is we can figure out the lengths of AB and the lengths of BC, which I'm going to call A and B respectively, just so it's going to fit nicely into our Pythagorean theorem. Okay, so finding the length of AB, well, you could intuitively just say, okay, well, it's not going anywhere in the x direction. It's going purely up. So the line segment is going to be exactly 2 units long. Hence, we know that side AB is 2 units, right? The length is 2. Alternatively, what you could do, you could use the distance formula. And you could use the distance formula in one dimension. Just because it's going up doesn't mean it's not just in one dimension, right? There's no x components that's moving our point B to A. It's purely in the y direction. So since B is directly at the origin, we know that B is going to be 0, 0. So the y component of that is just going to be 0. So 0 minus, and then the y component of A is also going to be 2, with its x component also 0, right? It's not moving, it's along the same axis, so we can just use our distance formula in one dimension. If you wanted to use the distance formula in 2 dimensions, you could absolutely do that as well. It's just more work, and it's just going to give you the same answer anyway. So we get the distance between B and A, so between 0 and 2, and we know that this is going to be 2. So once again, we have now shown that side AB is 2 units long, or the length of it is 2. Okay, we're going to do the same thing for side BC. So side BC is, well, I mean, you could already intuitively see it's probably just going to be 4 units, right? Because it's moving along the x-axis and only along the x-axis. So it's moving along the x-axis 4 units, so hence for its length, right? But once again, you can use the distance formula in one direction or 2 if you wanted to use the longer distance formula. I'm not going to because it's just doesn't seem like, fitting for the amount of time that we have. So we're going to say, okay, well, again, from the origin to 4. So this is going to be the absolute value of -4, and we know that that's going to give us 4. So great. So now we've shown that A is 2 and B is 4, right? So we're just going to plug into our Pythagorean theorem and see what we get. So we have A is 2, so we have 2 squared plus B being 4 squared is equal to C squared. And again, we're solving for C here, right? So we just need to isolate for C. So we get 2 squared being 4 plus 4 squared is 16 is equal to C squared. This is 20 is equal to C squared. And how do we solve for C now? Well, C is being squared, so we just need to take the square root of both sides, right? So taking the square root of both sides, we get square root of 20 is equal to c. And now this is kind of a point of confusion, especially given all of the topics that we just did. Do we have to put the plus or minus in front of the square root of 20 because we're solving for a variable? The answer is no. And the reason that the answer is no here is because distance cannot be negative. Keep in mind what we're solving for here, right? C is distance. C is the length between 2 points. And because length cannot be negative, we know that it's only going to be the positive value that we care about. Okay, so we can just forego the plus or minus because, we only care about the positive value here. So as a result, we can just simplify square root of 20, and we just did that earlier, and we saw it was 2 square root of 5 is equal to c. And we have now shown via the Pythagorean theorem that this is, in fact, the same thing, right? When we did our distance formula over here, we got 2 square root of 5, and we arrived at the same conclusion when we used the Pythagorean theorem, 2 square root of 5. Okay? Now, I feel like the part where some of you guys might have gotten lost is finding the lengths of each side. But once again, length is just the distance between 2 points, right? So I used the distance formula in one dimension, but I want to really emphasize if you were trying to solve for the length of AB, the line segment, which is right here, you could have used this really long distance formula in 2 dimensions, but you're going to see that it ends up being trivial because one of those components is just going to be 0 minus 0, right? The x components are 0 minus 0, which is 0 squared, and then you would just get 2 minus 0 squared, and then the square root of it. Well, that's what the absolute value is doing anyway, and you would just get 2, regardless. And then the same conclusion you could arrive at for side BC. So that's why I just used the distance formula in one dimension, because the other dimension is just trivial, right? There is no movement inside BC in the y direction. So we don't need to use the distance formula in 2 dimensions here. Okay, so hopefully that makes sense and that wasn't too bad for you. Okay, so given all that, let's go ahead and do one more example here with Pythagorean theorem, okay? So let's say we had, and I'm just going to clear off everything now. Let's say we had the points A being at 4, 3, B being at 1, 4, and C at, -2, -5. Okay. So given these 3 ordered pairs, what I want to see is with the triangle that they form, let's show whether or not this is a right triangle. Okay, so let's prove whether or not this is a right triangle. Okay, so the first step being, let's plot this onto a graph. So we're just going to do this. I'll make it a little longer. There we go. So give me 1 second. For you guys, it might be a little bit easier to do this. It takes me a little bit longer because I'm on a tablet, but that's okay. And there we go. Okay, pretty good. All right, so now we have to go ahead and plot A, B, and C onto our coordinate plane. So if this is 1, 2, 3, and 4, and we're going 1, 2, 3. Up our y-axis, so 1, 2, and 3, we know that A is going to reside right here at 4, 3. So we'll call this A. Okay, B is going to be at 1, 4, so that means we go 1 unit over in the x direction, so 1, and then 4 units up, so we're over here now, and this is going to be B. And C is going to be -2, -5. So because both of them are negative, we already know that this is going to be in the 3rd quadrant. And so this is -1, -2, and it was -2, -5, right? So -1, -2, -3, -4, and -5. So this means we are at -2 on the x-axis and 5 units down on the y-axis, which gets us somewhere right around here, right? And now what we have to do is this forms a triangle, these 3 points. So I'm just going to go ahead and draw the lines so that way we see that it's a triangle. So we have the triangle formed by these 3 points. That's one line. Here is my second line, and now my third line right here. Oops. Hurry up. There we go. Okay, great. So now what we have to do is, although this might not look like a right triangle, remember it's not drawn to scale, right? So we still have to see whether or not this is actually going to work or not. So we know, and again, I'm just going to write C down here. I forgot to label my point. Sorry about that. Okay, so what we're going to do is we're going to find the lengths of every side. And then once we find the lengths of every side, we're going to plug it into our Pythagorean theorem and see if it works out. So our goal here is we find the lengths of, side A, B, and see which one works out. And remember, your longest side, whatever side we find is the longest side, your longest side is going to be the hypotenuse. So that one is going to be your C. Okay, so we know automatically just from looking at this that length AB is going to be super small. So let's start there with the distance between A and B. So we're getting length by doing the distance formula first. So we essentially have to do the distance formula 3 times. And now keep in mind, there is in fact movement between both the X and the Y components. So that means we can't just use the absolute value distance formula because that's only in one dimension, right? Because we're moving in both X and Y from A to B, then we have to use the longer version of this. And we'll see we'll have to do that for all 3. So the distance between A and B is equal to, and let's see here, A was 4, 3. It would probably help if I actually wrote these out over here, right? So 1, 4, and this over here is -2, -5. So we're just writing them again on the graph just so I could see them for convenience. So I'm going to use A to be my first point. That's, the components are going to go first. You could use B. Either way, you should arrive at the same answer. So because my components of A are going first, we're going to have 4 minus whatever the X component is of B. So that's going to be 1 squared plus, and now, again, you remain consistent. So it's going to be the Y component of A. So it's going to be 3 minus the Y component of B, which is 4 squared. Okay, so now let's go ahead and simplify. So we get 4 minus 1 squared, which is 3 squared. So we have 3 squared here. Plus 3 minus 4 is -1. So -1 squared. We see here that this is going to be 9. So we get the square root of 9 plus 1 is equal to the square root of 10. And we can't simplify the square root of 10 anymore, right? So we just leave that as square root of 10. So we know that this side length is square root of 10. Okay, we now have to repeat this 2 more times, but now we're going to do side BC and side AC. Okay, so side BC, and we can even label these. So this is the side AB, and let's do the side AC now. So AC is going to be the distance between points A and C. And so we have the square root of, once again, I'm just going to remain consistent and have A be my, the components that go first. So for A, we have 4 minus -2, right? The X component of point C is -2. So 4 minus a -2 plus, and we have 3 minus, I believe it was -5, right? So the Y component of A is 3. The Y component of C is -5. So we have 3 minus -5 squared. Okay, so let's go ahead and simplify this down. We know that we're going to have the square root of 4 minus a -2 is 4 plus 2, which is 6 squared. So we have 6 squared plus, and over here we have 3 minus a -5, which is 3 plus 5. So 3 plus 5 is in fact 8. And so we have 8 squared over here. Okay, 6 squared is 36. So we have the square root of 36 plus 8 squared is 64. So we get the square root of 100, and the square root of 100 is 10. So we now know that over here, this side is 10 for side AC. And last but not least, side BC is the last thing that we have to do. So side BC, well, side BC is going to be the distance between points B and C. And I don't remember what the components are of B, so let me look back up top. the components of b are 1 and 4, right? So I'm going to make b go first. So we have 1 minus the negative 2 squared plus 4 minus negative 5 squared. It was 4, right? 1, 4. My memory is failing me. Yes, 1, 4. Okay, great. Okay, so now all we're going to do is we're once again going to simplify down. We have 1 minus a negative 2, which is 3 squared. So we have the square root of 3 squared plus 4 minus a negative 5 is 4 plus 5. So that's 9 squared. We get 9 squared over here. Okay, 3 squared is 9. So we get 9 plus 9 squared is 81. So right here. And this is going to give us the square root of 90. Okay, so what we can do is we can then take this out, right? So we can factor square root of 90. And the reason that I want to factor square root of 90 is because I want to have square root of 90 simplified down. So I know exactly how big this is in comparison to the other two sides, right? So square root of 90, well, that's the same thing as square root of 9 times 10. So this is going to be 3 square root of 10, right? You can break it up into the square root of 9 and the square root of 10. We know that we can't simplify square root of 10, so that goes in its own box, and the square root of 9 is just 3. So we know over here that we have 3 times the square root of 10. Okay, so 3 times the square root of 10. Okay, well, we know that BC is definitely larger than AB, right? Because AB is square root of 10 and BC is 3 times the square root of 10. So that's 100%. We already know that for sure, right? And then for side AC, if it's not immediately clear that it's larger, you just by inspection, well, you know that 10 is the same thing as square root of 100, as we just saw, right? And square root of 100 is really just square root of 10 times the square root of 10, right? And we know that square root of 10 is bigger than 3. Feel free to, double check that, but square root of 10 is in fact larger than 3. And we know that because 3 is the square root of 9, and square root of 10 is in fact larger than the square root of 9. So we now know that this side over here is our largest side, and since this is our largest side, this is going to be our hypotenuse. 10 is what we're going to be plugging in for C. So when we're all said and done, what we're going to be doing now is we're going to plug in the values that we just got, 3 square root of 10, square root of 10, and 10. And we're going to plug that into our Pythagorean theorem and see if it works. If it works, then we have shown that ABC, triangle ABC, is a right triangle. And our angle, we know which angle is going to be the right angle because it's going to be the angle that's opposing the hypotenuse, right? So it's going to be the angle that's opposing side AC, which is 10. And so it would be right here. Okay, but because we haven't proven that yet, we can't say that yet. So what we have to do is we have to go to our Pythagorean theorem and we say, okay, a squared plus b squared is equal to c squared. Remember, it doesn't matter which leg you choose to be a and which leg you choose to be b. So I'm just going to say this is the square root of 10 plus, squared, plus 3 square root of 10 squared. And again, c is our longest side, so 10 squared. Okay, so plugging this in, we now get square root of 10 squared. Well, the square and the square root are just going to cancel, right? And we're just left with 10 plus. Okay, now the square applies to both the 3 and the square root, right? So we get 9 times 10, right? Square root of, 3 squared is 9, and the square root of 10 squared just gives you back 10. So we have 10 plus 9 times 10 is equal to, and then 10 squared is 100, right? So 9 times 10 is 90. Remember order of operations, you do multiplication first. So you get 10 plus 90 is equal to 100, and yeah, 100 is equal to 100. So this works, and because this works, because the legs added together when they're squared is equal to the longest side squared, we now have shown that triangle ABC is in fact a right triangle. So we can put that right angle there at angle B. Okay, because again, it's the angle that's opposing the longest side, which is side AC. Okay, so let's recap what we did here so that, it makes a little bit more sense. So our game plan to trying to prove that triangle ABC was a right triangle was we knew we would end up using the Pythagorean theorem, right? If the Pythagorean theorem works out, then the triangle is a right triangle. Again, they imply each other, right? If it goes in that way, and then also if the triangle is a right triangle, then Pythagorean theorem should work out. So they imply each other. Okay, so if that's the case, all we had to do was we had to get the lengths of each side. And once we got the lengths of each side, we just had to plug into our Pythagorean theorem. Well, finding the lengths of each side, it just means finding the distance between, all of the different point pairs. So that means between A and B, between A and C, and then between B and C. And we found our solutions for all of them. And probably the hardest part is just figuring out which one is the hypotenuse, but using a little bit of intuition and also, a little bit of math trickery. Remember, again, we showed that 10 is really just square root of 10 times the square root of 10, right? Or the square root of 100, and then we broke it up that way. And we know then that all we really have to see is if the square root of 10 is larger than 3, well, 3 is square root of 9. So obviously the square root of 10 is bigger than square root of 9. So yeah, so we've then shown that side AC is bigger than side BC. Okay. Again, that was probably the hardest part of all of this. And if you still don't understand that, feel free to reach out to me privately, and I'll be sure to, go through it a little bit slower, just to, really make sure that it makes sense. But that's the game plan. So now we found that side AC was our hypotenuse, and that's perfect for us because now we just go down here to our Pythagorean theorem and plug everything in. And once we plug everything in, we found that we got the same number on both sides. We got, the a squared plus b squared really did equal c squared. So triangle ABC was a right triangle. Okay, so with all of that being said, I want you guys to do the exact same thing with the following coordinates. Okay, so there's a triangle with the following vertices. We'll say 6, 2, negative 2, 0, and 1, 5. Okay, so given these three vertices or given these 3 points of the triangle, I want you to go ahead and see whether or not this is a right triangle. Okay, so your first step, if I were you, I would label these A, B, and C, so that way you have, a clear indicator of which sides you're solving the distance for. So you can label that, any of them A, B, and C, or whatever letters you want to call them. So that would be my first hint to you, and then go ahead and do distance, and then plug into your Pythagorean theorem. So I'll give you a couple minutes, or take however long you need, and then unpause the video when you are ready. Okay, so again, the first thing that I'm going to do, like I had mentioned, is I'm going to just label these, right? And I'm just going to label them in any order. So I'm going to call this A, I'm going to call this B, and I'm going to call this C. Next thing that I'm going to do is I'm going to sketch these onto a, oh, did I hit the bottom of this? Whoa, I've never hit the bottom. That's very strange. Okay, sorry. Let me scroll way up and rewrite this. I've never hit the bottom before, and I guess I went too far down. Okay, so A, once again, is 6, 2. B is negative 2, 0. And C is 1, 5. So 1, 5. Okay, so now let's go ahead and put this onto our coordinate plane. So let's draw that first. Coordinate plane. Okay. All right, not bad. Great. So now we have to go ahead and plug in the following pieces. So we know that we're going to have a piece at negative 2, 0. So negative 2, 0. So this is negative 1, negative 2. So right here. And negative 2, 0 was, what do we call that? We call that B. Okay, so this is going to be B. And actually, just for the sake of being able to see things better, I'm going to start using different colors. I realized that in the last example, that might be beneficial. So I'll write the letters in a different color. So C B is right there. Okay. Okay, so now we have to go ahead and plot the other ones. So 6, 2 and 1, 5. So we go 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, so for 1, 5, we know that we're going to be at 1 here, and we're going to go up 5 units. So right about here is going to be 1, 5. And this is point C. And our last piece is 6, 2. So 6, 2 is 6 units on the x-axis, and then 2 units up. So here's 6 units here. 2 units up is going to be right here. And we will call this A, as I have it listed above. Again, if you have different letters, that's totally fine. I'm just saying A, B, and C, and that's just how I'm going to identify them. But if you either mixed up the letters and they're different than mine, or you use different letters altogether, as long as you have a way of identifying them, that's totally okay. So we now have A, B, and C plotted. Great. So now what we have to do is, again, these are vertices of a triangle. So let's go ahead and draw the sides. So drawing the sides here, just give me 1 second. Okay, so we are going to draw that one. We are going to draw this one. And I know I went a little bit over, but it's not the biggest deal, as long as you guys understand it's supposed to stop at the point. So as such, and one more. Come on, ruler, work with me. All right, and there we go. Okay, great. So we now have our triangle made, right? So now what we have to do is, given the vertices that we had, so again, writing this one more time. So this is 6, 2 here. This is 1, 5. And over here is -2, 0. What we have to do is we have to find the lengths of each sides, right? And then our longest side is going to be what we're going to be plugging in for our hypotenuse. And then we're going to see if both sides check out. So our game plan right now is we're going to find the side. So first I'm going to find the side of AC, the length of side AC. So AC is going to be the distance between points A and C. And that is going to be the square root of, okay, so I'm going to start with my point A being first. Again, just be consistent in what you're picking. So I'm going to have 6 coming first, minus 1, right? So the x component of C is 1. So 6, 1 squared plus, and now the y components starting with a's. So we have 2 minus 5 squared. All right, let's simplify this down. 6 minus 1 is 5 squared. So we have the square root of 5 squared plus 2 minus 5 is -3 squared. And we see here that we're going to get the square root of 25 plus 9, which 25 plus 9 is square root of 36. And the square root of 36, wait, 36, is that right? No, I'm sorry, 34. Ooh, that would have been a bad mistake to make. Okay, square root of 34. Went too fast there. All right, so we have the square root of 34. Now, in previous examples and also previously in the lecture, I told you guys to go ahead and simplify the square roots down. You can actually just leave them as square roots, because when you plug them into your Pythagorean theorem, well, what's going to happen? The squares are going to cancel with the square roots, and you're just going to have the number underneath, right? You could simplify this down if you really wanted to, but, why is the question that you have to ask yourself. So we just leave it at square root of 34. Okay, so now let's go ahead and do a different side. So we had side AC, now let's go ahead and do side AB. So side AB, and this looks like, according to how we graphed it, this looks like it would be the longest side. So AB is going to be the distance between points A and B. And this is going to be the square root of, well, once again, I'm going to have my A come first. So 6 minus a -2. So we have 6 minus a -2 squared plus, and now we have 2 minus, right? 2 is our y component, minus 0. 0 is the y component of B. So we have 2 minus 0 squared. And let's simplify this. 6 minus a -2 is 8 squared, which is 64. So we have 64 here, plus 2 minus 0 squared is, well, 2 squared, which is just 4. So we have the square root of 68. Okay? All right, once again, this is where I'm telling you guys, just leave it as a square root, because it's just less work when you plug it back into your Pythagorean theorem. So now we have found the square root of 34 is equal to side AC. And we also have square root of 68 is equal to side AB. So now we just need to find side BC, right? So this side here, this is the last one that we have to do. And let me go ahead and just write in the lengths as we go, because I didn't do that. So this is square root of 34. This length over here is the square root of 68. Okay, so now moving on, we have one last length that we have to find. And the last length that we have to find is, again, BC. So side BC is equal to the distance between B and C. And let me see which one we want to go first. Let's go ahead and make C the piece that we're going first. So that means that we're going to have the square root of 1 minus a negative 2 squared. Okay, and this is going to be plus 5 minus 0, right? And let's just double check. Again, the y component of C is 5, the y component of B is 0, so it's 5 minus 0 squared, which is exactly what we have. Okay, let's simplify down. So we now have the square root of 1 minus a negative 2 is 1 plus 2, so that's 3 squared, which gives us 9. And 5 minus 0 is just 5. 5 squared is 25, so we get 9 plus 25. And once again, 9 plus 25, we see that we get square root of 34 again. So we have square root of 34, and we're going to write that over here. And if you guys are not sure what kind of triangle this is actually an isosceles triangle. Isosceles means that two of your legs are equal to each other as far as length is concerned. So we see here that this side is actually equivalent to this side, square root of 34 twice. But don't worry about that. That'll come much later as far as, isosceles triangles are concerned. We don't have to worry about that right now. So for right now, just worry about whether or not this is a right triangle. And we're trying to see, square root of 68 is obviously going to be the largest side, right? So we're trying to see if this angle right here, angle C, we're trying to see if this is a right angle. If that's a right angle, then great. We have ABC is a right triangle. So what do? We plug everything into our Pythagorean theorem. So our Pythagorean theorem is a squared plus b squared is equal to c squared. Your C is the longest side, right? That's your hypotenuse. So our longest side is square root of 68, and it's, of course, being squared. And your legs, we can put them in either order. And in this case, it really doesn't matter the order because they're identical, right? So it's square root of 34 squared plus, again, square root of 34 squared. Okay, well, what's going to happen when we square all of these? Well, the square roots are just going to drop out, right? So we see the square root drops out with the square 3 times, right? And what we're left with is 34 plus 34 is equal to 68. And yeah, 34 plus 34 is in fact 68, so we get the same thing on both sides. In fact, we have now shown that because the Pythagorean theorem works out, our triangle is in fact a right triangle. So yes, triangle ABC is a right triangle. Okay, so hopefully that wasn't too bad. Again, the entire game plan is you find the lengths of each sides, you use the distance formula to do that. Whether or not you use the distance formula in 1 dimension or the distance formula in 2 dimensions entirely just depends on whether or not there's a movement in both axes or just one axis, right? If, for example, just hypothetically, and I'll draw this in red, if hypothetically A was right here on the x-axis, then to find the distance between A and B, you're just going across 1 dimension, right? You're only going across the x-axis. So as a result, you could just use, the smaller distance formula, which is just the absolute value. But because there's also movement in the y direction, it's going up, right? Then we have to use the real distance formula, which is, the square root of the components being subtracted and squared, and then added together. So in this case, we did it 3 times. We found that we had the square root of 34 twice for our legs. We had the square root of 68, and because that was the longest side, we use that for our hypotenuse. We plug it into our Pythagorean theorem, a squared plus b squared is equal to c squared. And since we got the same thing on both sides, we can conclude that triangle ABC is a right triangle. Okay, so there's one last topic that I want to go into today. And the last topic I want to go into is called the midpoint of a line segment. Okay, so say we have a line segment, and a line segment is essentially just when you have 2 ordered pairs and you're talking about the distance between those 2 ordered pairs, right? So any line segment is just the length between 2 points. Well, if you have any line at all, doesn't matter how long, any line segment, doesn't matter how long or how short that line segment is, you're always going to have a midpoint of it. Even if it doesn't look like it, even if, just hypothetically, we just had this as our super tiny, super short line segment, right, where I'm trying to draw points here, you would technically have a midpoint of this It's just, you might not be able to discern it with your, just with your human eyes, right? But it does exist. So the way that we find a midpoint is essentially we take the average of the components. And now keep in mind what I was telling you before. The distance formula is going to return a number, right? Because a number is going to tell you the length between the points. A midpoint is going to return a point. It's going to return an ordered pair. The reason is because a midpoint lies halfway between whatever your two endpoints are of the line segment, and it lies on that line segment, okay? So the way that we find midpoint is, once again, we're essentially taking the average of each component. And what does it mean to take an average? Well, if we have only two things, right, we have two points. So if we had, a line segment, we'll call this P, and it's going to line segment, or I'm sorry, it's going to point Q, then the midpoint M, and this is not drawn to scale, the midpoint M is just going to be the average of the X components added together and then the Y components, right? So then it's just the average of each component of P and Q. So we say our midpoint formula is as follows: x1 plus x2 over 2, right? Because there's only 2 points that we care about, P and Q, we just divide it by 2, and then we've taken the average of it, right? We've taken the average of the X components. And we do the same thing for Y. So y1 plus y2 divide by 2. And this is your midpoint formula. So let's go ahead and do a quick example together. So let's say that we had the midpoint of a line segment whose endpoints are P, so 5, -2, and Q, so Q being 6, -1. So if we really wanted to, we can draw this on a number line, or I'm sorry, on our coordinate plane, right? So drawing this on our coordinate plane, and I'm not going to bother with the ruler. I'm just going to try to do this as best as possible. So 5, -2, it's really going to be over here. So our points are going to be in the fourth quadrant. So let's just say this is 5, and then this is 6, right? So 1, 2, 3, 4, 5, 6, great. Okay, and then we have -1, -2. Okay, so 5, -2, and I'm actually going to write these above here. 5 and 6. 5, -2 is going to be right over here, and 6, -1 is going to be right over here, right? So again, it's a fairly small line segment, but that doesn't mean that there's not going to be a midpoint. So we draw the line segment. Great. So we're looking for the midpoint, which is the point that lays halfway between both of them, right? So if this is P, this is Q, M, our midpoint, lies directly halfway between them. So finding this, all we have to do is we plug into our formula. So we have M is equal to, and our formula is we add up the X components and we divide them by 2. We add up our Y components and we also divide them by 2. And whatever we get for, our X component and our Y component, well, that's going to be our ordered pair, right? So in this case, we're adding up our X component 5 and our X component 6, and we divide them by 2. So we have 5 plus 6 divided by 2. And now we do the same thing for our Y components, right? So our Y components are -1 and -2. So we're going to add those together as well. So we have -1 plus a -2 divided by 2. Okay, so now we just simplify. So simplifying, we get 11 over 2. Here, right? 5 plus 6 is 11 divided by 2. Well, 11 is not even, so we can just leave it as 11 halves. And over here, -1 plus a -2 is the same thing as -1 minus 2, so it's becoming more negative. And we get -3 over 2. And this is our new ordered pair, so this is our midpoint. Okay, and if you aren't sure what this really means, well, do the actual division. And again, this is one of those times where a decimal may actually help you instead of a fraction. So this is the same thing as if we had 11 divided by 2 is really 5.5. And for -3 divided by 2, well, that's just -1.5, right? So what does this really tell us? Well, if we go back and we look at this, why does 5.5 make sense for our average of our X component? Well, notice it's halfway between 5 and 6, right? We moved 0.5, away from 5, and also 0.5 away from 6. So 5.5 should make sense. And the same thing with -1.5, right? We moved a half away from -1, and we also moved a half away from -2. They just went in, different directions. So we can now say our midpoint here and our final midpoint is, in fact, 11/2 and -3/2. And you don't have to write it over here on your coordinate plane. I just did it to really reinstate where our midpoint is lying. Okay? And this would make sense if this were drawn to scale, but just bear with me. Notice that 5.5 would be right about there, and -3.5 would be right about there, right? So I'm sorry, -3/2 would be right about there, -1.5. So we see that our midpoint really does make sense, and we do have a midpoint of a line segment. So your last classwork assignment is just to practice, figuring out the midpoint. Whether or not you want to draw it on the coordinate plane, that's totally up to you. For the purpose of this classwork assignment, number 3, you don't have to. I just want to make sure that you understand how to find the midpoint. So given points P, which are -3 and 6, and Q is 1, 4, find the midpoint of this line segment made by these 2 points. I'll give you, 1 or 2 minutes, and then we'll get going. Okay, and when I said I'll give you, I meant, take 1 or 2 minutes. But anyway, so our midpoint equation is defined as the average of the x components and then the average of the y components, right? So if the average of the x components, well, we just add them together and then divide it by 2. So we have -3 plus 1, -3 plus 1 divided by 2, and then 6 plus 4 divided by 2. And, well, it's really that easy, right? -3 plus 1 is -2/2. So we get -2/2. And over here, we get 10/2, right? 6 plus 4 is 10. And then simplifying, we end up with -1 and 5. And does this make sense for us to get -1? Well, sure, right? If we're talking about the distance, let's only talk about the x component, right? So the x components are, we're starting, so if here's 0, right? 1 is right here. Then we have -1, -2, -3, right? And our x component for P was -3. Our x component of Q was 1, right? So halfway between the two, well, that's just 2 steps away from, both of our starting places. So we started at -3 for P. We're starting at 1 for Q. And so this is 1, 2, right? And then also this one is going 1, 2. So we ended up at -1 because -1 is halfway between -3 and 1. So that's how we got here. And now same thing for 5, right? We got 5 because 5 is halfway between 6 and 4. You moved 1 unit away from 6, you moved 1 unit away from 4. And so that's how we're arriving at our midpoint. That's why we take the average of them, because we're, seeing what the halfway point really is. And then we put them together, you smack them into one ordered pair, and you get -1, 5. Okay, so hopefully that's not too bad. I know I went a little bit over in today's lecture, but we got through the whole chapter, which is what we wanted, well, what I wanted to do, maybe not what you guys wanted to do, but it's what I wanted to do. So we got through the whole chapter, so this one is done. So now next time we can look at, if you guys are following along in the book, again, I told you the book wasn't really necessary unless you really wanted it or unless you already bought it. But if you are following along in the book, the coordinate plane chapter that we just did is chapter 2.1, and the next one that we'll be looking at in our next lecture is 2.2. Okay, so thank you guys for participating, for your added patience with everything that we've been doing, and I wish you all a great rest of your day. That about does it for me. So have a good one. I'll talk to you next time.